So today we'll be starting with frequency measurements. So we have already studied so far phase measurement using power factor meter devices. So now we'll be looking at the frequency measurement techniques, how we can measure frequency using different available devices. There are a number of types of frequency meters. These are number A. We have the mechanical resonance type. Secondly, we have the electrical resonance. We have the electrical resonance type. Thirdly, we have the electrodynamometer. The electrodynamometer type. And fourthly, we have the Western type. Number 5, we have the ratiometer type. And lastly, we have the saturable core type. So frequency can be measured with any of these different types of meters available to us, and we can also use these are different analog devices: the mechanical resonance type, the electrical resonance type, the electrodynamometer type, ratiometer, saturable core type, and we have other digital devices like the electronic counters, frequency bridge, stroboscopic methods, or CROs extra. So those are the digital metering devices, the oscilloscopes, the electronic counters. So using those we can digitally measure the frequency. So we'll be going through all of these one by one. We have the mechanical resonance type first, or what is also known as a vibrating reed type. So first of all, looking at the construction of a mechanical resonance type, or what's also known as the vibrating reeds. So the construction is such that we have these reeds. They are simply steel strips. A number of reeds, they are placed, they are aligned to each other, assigned in a particular fashion, and assigned in close proximity to this electromagnetic core. There's an iron core, that's laminated magnetic iron core, which is carrying the windings also. Right. So you have the reeds. They are simple steel strips placed alongside this electromagnetic core made up of iron that's also supporting the windings. These reeds are actually fixed at the bottom, while as they are free at the top. And they are known as the flags. Now, construction wise, also speaking, these reeds are actually placed. These reeds will not be of similar size and shape. They will be of different sizes and shapes, different size and weight. So since the reeds are free at the top end, so there will be a vibration caused in these reeds. So now the natural frequency of oscillation of these reeds will actually depend upon the size and the weight of the reeds. Now these reeds are we specifically choose these reeds to be of such size and such weight that the natural frequency of oscillation of these reeds varies by 0.5 hertz from reed number 1 to reed number n. Fine. So say for example, this reed is the natural frequency of oscillation of this reed is 47 hertz. In that case, this reed will be vibrating at 47.5, then 48, 48.5, 49, 49.5, and this can be vibrating at a natural frequency of 50 hertz. Fine. So construction wise, simply there are steel strips known as reeds placed alongside an electromagnetic iron core that's laminated also and carrying the windings. The reeds are fixed at the bottom and they are free at the top end, and these reeds are coming in different size and weight. The dimensions will be different, the weight will be different, and such that the natural frequency of oscillation subject to any vibration will cause the reeds to vibrate at this particular frequency in this ascending order. The size, the dimensions will be placed, that will be ascending, that will be placed in such an order that the natural frequency of oscillation is also ascending in it is actually an ascending getting an ascending simply stating that if the first reed is oscillating at 47 hertz, the next will be oscillating at 47.5 and the next at 48, and ultimately you will have one reed that's oscillating at 50, another at 50.5, and so on. Okay, now moving on to the operation of this particular frequency meter device. So what happens here is that keeping the figure in mind, we are applying a rated voltage to the windings, or we can say that a rated current is flowing through the windings. So the frequency, we are having an AC current, so its frequency will be same as that of the supply. Fine. So our AC current is alternating through the windings. It's alternating at the same frequency as that of the supply voltage. Now this core will act as the electromagnet that we have already said. It will attract the reeds. So the reeds will start vibrating with respect to the electromagnet. Now what will this frequency, what will be the rate of this vibration will actually depend upon I square. In other words, the rate of vibration of the reeds will be proportional to supply frequency square. So it will depend upon the supply frequency, and at that rate the vibration of the reeds will occur. So simply stating, we are supplying the windings of this windings arranged around this core at a rated we are applying a voltage to the windings of the core, and it will be carrying a rated amount of current at the same frequency as that of the supply. Now this core will act as an electromagnet, and it will attract the reeds. So reeds, since they are they are movable at one end and they are attached, they are fixed at one end, so a vibration, so these reeds will be vibrating with respect to the electromagnet. So this rate of vibration is actually proportional to the current square, or in other words we can say to the supply frequency square. Now what will happen is that each and every reed will vibrate at depending upon its natural frequency of oscillations, but the particular reed whose natural frequency of oscillation will be equal to the supply frequency, it will that particular reed will be in resonance with the electromagnet. That particular reed will be in resonance with the electromagnet, and that means this particular reed will have the maximum amount of oscillations. So each and every reed will be oscillating depending upon their natural frequency of oscillation, but this particular reed whose natural frequency of oscillation will be equal to the supply frequency will be in resonance with the supply voltage, supply frequency, and that means this particular reed will be vibrating the most. Also you can understand that this force that will be acting on the reeds will be applying every half cycle. So all the reeds will tend to vibrate, but the reed whose natural frequency is equal to the twice the frequency of supply, because we are having f square here, will be in resonance with the and will be vibrating the most. So we can actually plot this resonance curve, which will actually show us the variation of the oscillation, the magnitude of the oscillation with respect to the frequency of oscillation. So just like any other resonance curve. So noting out the other characteristics of this particular device, we have the frequency range. So typically this device measures any frequency between 7 Hz to 53 Hz. So this is actually an indicating device wherein we have our system will be our reeds will be vibrating at the natural frequency of oscillation when attracted to the electrodynamometer, but that particular reed that will be vibrating the most will actually be vibrating the most because it will be in resonance with the supply frequency, the twice the supply frequency. So noting down that we have one device, then one particular reed that is having the most amount of vibrations, and knowing its natural frequency of oscillation, we are already aware about the natural frequency of oscillation of all the reeds, knowing their size and their weight extra. So we can this particular read will give us an indication about the frequency of the supply voltage. So the frequency span, the normal frequency span is somewhat between 7 Hertz to 53 Hertz, and this can be actually doubled with can be doubled by changing the number of reads, or doubling the number of reads. So what are the advantages of this mechanical resonance device? Or is that the indication will actually be independent of the supply voltage, and and that means basically that it means that the oscillation is independent of the vibration of the reeds is independent of the magnitude of the applied voltage. It only depends upon the frequency of the applied voltage. However, there is a disadvantage of associated with this system, and that is the reads have a difference in measurement of 0.5 Hertz. So you have 50 Hertz, you have 50.5 Hertz, you have 49.5 Hertz. So the system can only resonate at 49.5 Hertz or 50 Hertz, double at these frequencies, at the natural frequency 49.5, 50, 50.5, but it will not resonate at 49.75, 50.25 or 50.23. So precision measurement using this device is not possible. We can only measure fixed set of values that are actually differentiating in the range of 0.5 Hertz. So this is a simple device. You have an electrodynamic, you have an electromagnet that basically is a iron core around which is a winding. This winding is supplied with is actually a voltage applied to the winding, so that rated amount of current flows through the windings, and the current is alternating at the same frequency as that of the supply voltage. The reeds, they are steel strips fixed at one end and free at another end, so they oscillate, and then the reeds are such placed that the natural frequency of oscillation is differentiating by 0.5 Hertz with every reed. Right? So if the first reed is oscillating at 47 Hertz, another one will be oscillating at 47.5, then 48, and 48.5, and so on. And we know that these reeds will be attracted to the electromagnet as soon as the electromagnetic is excited. So they will vibrate. Proportional to the current square, or you can say frequency square. So whatever is now, if a particular reed is in resonance with the supply voltage, the supply frequency, that means the maximum amount of vibration will be caused in that particular reed. So that will give us an indication about what is the value of the applied frequency of the supply voltage, frequency of the applied supply voltage. So next we have the electrical resonance type. So in the electrical resonance type, there are again two types of meters. One is the ferrodynamic type frequency meter construction, and another one is the Western type frequency meter construction. So first one, we have the ferrodynamic type frequency measurement construction, and the construction diagram of this particular meter is shown here. So it basically consists of a fixed coil, which is simply connected to the supply voltage, to the supply circuitry around a laminated iron core, and this laminated iron core is it is actually in coordination with the pointer and the pivot system. So you have the fixed coil here. It's also known as the magnetizing coil. So it's connected to the supply, across which the voltage will be applied, whose frequency actually we are trying to measure. So this coil is wound around a laminated iron core, and we have a moving coil system that is pivoted alongside the pointer, and also attached with this moving coil is actually in parallel capacitor. So the moving coil is actually connected to a capacitor. So you have the fixed coil and you have the moving coil. So the magnetizing coil will actually produce the magnetic field that will be linked with the moving coil. So what happens here is you have we are applying a current I. We are applying voltage to the magnetizing coil. It will produce current I will be flowing through this magnetizing coil. That will result in the production of electromagnetic flux. This magnetic flux will get linked with the moving coil. It's not moving yet, so it will induce EMF in this coil, and since you have a current carrying conductor now placed in a magnetic field, it will experience a torque. So this moving coil will start rotation. Now this rotation will actually be proportional to the amount of current being, and as well as the flux being linked with this moving coil. So we will have three different scenarios. Assume this is our current I flowing through the magnetizing coil. The flux that will be generated by this magnetizing coil will be in the same phase as that of the current I. Now if we assume this particular current is inducing an EMF E in the moving coil. This EMF E will be 90 degrees behind the current I because it's capacitive in nature. Now what will be the value of current? What will be the current flowing through this moving coil? But that will be dependent upon the value of the capacitance as well as the value of the inductance of the magnetizing coil. Of the moving coil. There is a current capital I flowing through the magnetizing coil, and there is a current small I flowing through the moving coil. The EMF induced in the moving coil will be 90 degrees behind the main current, but the current I that will be flowing through the moving coil will now depend upon the inductance and the value of capacitance of this moving coil. So you can have three different scenarios. We can have a scenario where E is in phase with this current. We can have third scenario where E and I is actually lagging behind the E. So you have this case where the circuit is purely capacitive, the moving coil circuit is purely capacitive, or it's purely not purely capacitive, but it's capacitive, it's purely resistive, or it is more inductive. So in the inductive case, the current small I that's actually flowing through the moving coil will be lagging behind the induced EMF. In the resistive circuit, small I and E will be in phase, and in the capacitive circuit, small I and E will be the current will be actually leading the induced EMF. So in all the three cases, what will happen is that the torque that will now be applied will be the deflecting torque that will be applied will be proportional to cos of 90 plus alpha. In the second case, where we have actually the moving coil is it will be proportional to the main current flowing through the magnetizing coil, proportional to the current flowing through the moving coil, and proportional to cos of 90 minus alpha, where alpha is the angle between E and I. And in this case, it will be simply cos of 90. Cos of 90 is 0. So in this case, the deflecting torque will simply be equal to 0. So hence the deflecting torque in case on the moving coil will be 0 when the inductive reactance is actually equal to the capacitive reactance, or we can simply say this circuit is purely resistive at that time. So at that time there will be no deflection of the pointer. So you can see we can have a positive deflection, we can have a negative deflection, or we can have a zero deflection of the pointer depending upon the nature of this moving coil, whether it's inductive in nature, whether it's capacitive in nature, or whether it is a resistive circuit in nature. So that's all about this ferrodynamic type frequency meter device. So we have studied today the magnetic resistance type and the electrical resistance type. We still have the electrodynamometer type, the Western type to study. That we'll do in the next session.